So I want to talk through problem 23. It's a very basic problem, but I'm seeing all sorts of inconsistencies in students' solutions. So here's the problem with the bucket of water. So here's a picture of the bucket, and of course we're going to draw a free body diagram, but before we do that, we do all the information off to the side. So the bucket is being raised, so it's moving up, and it's got an upwards acceleration, it says so, and the acceleration points up, the net force points up, it's moving up, so I'm calling up the positive direction, all the usual stuff. We draw the free body diagram. We start with weights pointing straight down, of course. Then we draw the tension, because it's in a rope, there's going to be a tension force, and we know the tension points upwards, because strings and ropes only pull. But how long should we draw the tension vector compared to the weight? Well, we look at our information off to the side. We know it's accelerating up, we know the net force points up, which means the upward force has to win, and so we're going to draw the tension force larger than weight. Okay, and our job here is to find the force exerted by the rope on the bucket. In other words, we're finding the tension force. Okay, up to this point, everything's going well, but then I start to see all sorts of weird things in students' solutions. Things that students are doing, they've convinced themselves they're doing things correctly, they even might be getting the right answer, but it's not correct, okay? So here's one of the things I'm seeing some students do. They're doing something with like a total acceleration. Here I'm using air quotes. You can't see me using air quotes, but I'm doing it, okay? They're putting the 9.8 meters per second squared together with the 3.0 meters per second squared given in the problem, or perhaps they're subtracting them for some reason. And so students have sort of convinced themselves that maybe they have to combine accelerations. Now, you'll never see me do this. Why will you never see me do this? Because we shouldn't. We don't do this. This is wrong. This is completely and utterly wrong. Even if it ends up getting you the right answer, it's wrong. Why is it wrong? Well, because we don't do this. We don't combine accelerations. Some students have convinced themselves that somehow you have to combine the acceleration given the problem with the gravitational acceleration to get the real acceleration. That's not true. If the problem tells you the acceleration is 3 meters per second squared, they're not lying to you. That is the acceleration. And by doing this, you might be convincing yourself that something else is happening here. And then if later on in the problem they ask you to find how far the bucket went, how much time it took to go somewhere, how fast it's moving, you might be tempted to use an acceleration that combines the acceleration due to gravity and the acceleration given, and that's wrong. When they tell you the acceleration is 3 meters per second squared, it's 3 meters per second squared, and that's it. They're not lying to you, so trust me, if you're doing anything with this with like a total acceleration, it's wrong. You've got to go back and fix it. It's not right. Okay, then some other things I'm seeing some students do. Things like this. They start with sigma F equals ma. Fantastic. That's a great start. You know I love that equation. Then they do this, plus mg. Now, I don't know why they're doing that, because you'll never see me do this, or maybe they subtract mg. And I don't know why students are doing this, because it's wrong, right? It's completely wrong. In fact, it actually hurts me to say it out loud. It hurts me to write it on the PowerPoint, because this is not right. Newton's second law says sigma F equals ma, and that's it. If you ever find yourself doing sigma F equals ma, and then right afterwards you're doing plus or minus anything, it's wrong. It's really, really wrong. Even if, again, you seem to be getting the right answer and you've convinced yourself you're doing it right, trust me, it's not right. Sigma F equals ma, and that's it. There's nothing to add to that. You should never, ever be finding yourself writing sigma F equals ma plus or minus anything. It's really, really wrong. Okay, so then some students did this. They just found sigma F equals ma. They did the mass times the acceleration. They found 15 newtons. That's great. And some students left it like that. Now, at that point, you're saying to me, you're not checking your answers, because you see the answer is not 15 newtons. The answer is 64 newtons, right? And so if you just left it like this, not only do you not understand what you're doing, but also you're not checking your answers, or you don't care if you're getting it wrong. I'm not sure, or you're not quite sure what to do next. So some students may have checked their answers and said, oh, I only got 15 newtons, but I see the answer is 64 newtons. I know I will take that and add it to the weight, because, oh, look what happens. When you add the weight, 5 times 9.8, which is 49 newtons, lo and behold, you get 64 newtons, and you box it in, and you're done. And you think, I've solved the problem correctly. But it turns out you haven't. How do we know we've not solved the problem correctly? Because look what we've written here. It says sigma F equals 64 newtons. Look what the problem asks. Does the problem ask you to find sigma F? Well, no, it says find the force exerted by the rope on the bucket. And so even though mathematically you have a correct answer, you don't know what you're doing. Finding sigma F when it doesn't ask for sigma F is wrong. It's wrong. It really, really is wrong. Now, the previous one is not wrong, it's just not the right answer, right? So there's nothing actually wrong with finding sigma F as 15 newtons, it's just that that's not what the problem asks you to do. The problem asks you to find a force, the specific force exerted by the rope. That's called tension. And so Finding sigma f is not the answer. Finding sigma f and then adding the weight is also wrong because look, that's the exact same thing as this. That's sigma f equals ma plus mg, isn't it, right? Here's ma, 15 newtons. Here's mg. It's literally doing the same thing we did above. It's wrong. So what is the right way to do it? Well, luckily I've established a certain routine for this, haven't I, right? So we draw the free body diagram, we establish a positive direction. What do we do next? We write sigma f equals ma, and that's it, right? We don't add anything to it. But what's the very next step? The very next line down, we look at our free body diagram, we list each of the forces with their proper sign. We see tension is pointing up is positive, so it's positive T. We see mg pointing down, but up is positive, so it's minus mg. And that's it, right? Isn't that always the next step? It's always the next step. This is what we always do. We go from sigma f equals ma to the very next step of listing the forces with their percent. What do we do next? We solve for what we're looking for. In this case, it's going to be tension, so we just do our algebra, rearrange this. This is T equals mg plus ma. At this point, you're solved for tension. You must be doing correctly, okay? Now, compare this to sigma f equals ma plus mg. Notice that it's not the same thing because this solves for tension. Tension is what we're looking for. Saying sigma f equals ma plus mg, we know is wrong because that's not Newton's second law. It never will be, right? And so that's a big difference between a force, tension, and net force. All right, now at this point, you may remember I've done problems like this before where if you want to pull a mass to the outside, algebraically make it look a little more sophisticated, you get something that looks like this. T equals m times the quantity g plus a. That's just good algebra there. And this is again where some students get confused. They say, oh, g plus a. I know that means the real acceleration is like this over here, right? 9.8 plus 3. There's justification for adding accelerations. No. In fact, from the very first time we saw this, I tried to make it very, very clear. Even though algebraically it looks like we're adding accelerations, we're not, right? Look at Newton's second law. Does it say sigma a? Does it tell you to add accelerations? No, it does not. It says sigma f. It tells you to add forces, and that's what we did. We combined the forces, and the combined effect of tension and weight produces an acceleration, in this case, of 3 meters per second squared. This step down here is just algebra. If you pull a mass to the outside, you happen to get an algebraic expression that makes it look like we're adding accelerations, but trust me, we're not. And as I said the first time we saw this, if this confuses you, if it's bothering you, if you think that you're going to add accelerations, then don't even write this step. Don't even bother with it. Just stop right here. T equals mg plus ma, put your numbers in, and be done with it. But again, you'll notice that even all these wrong answers here may get you to an answer that looks correct. You may have convinced yourself that you've done it correctly because you have a right answer. They're wrong. And so you really want to go back to this particular problem and see, did you do any of these? If so, correct it, do it correctly, and then look for this sort of incorrect way of doing it in other problems, because I guarantee there are going to be other places where this happens, specifically with vertical motion is when it happens the most because of the force due to gravity and then the acceleration due to gravity, and students, again, sort of convince themselves they think they have to do something by combining accelerations. But it's not limited to this, so please do go back to all of your work and see, have you been doing things like this? And you should be correcting it. Remember, we follow a routine because it always leads you to the correct solution.